There's a lead pipe on a Turkish mountainside laid down about 2,200 years ago, and the water inside it is under enough pressure to split a modern garden hose, roughly 275 pounds per square inch, several times more than what's behind your kitchen faucet. The pipe is cast lead, hand-poured, and sealed section by section. The people who built it had never seen a pump. They had no motor, no pressure gauge, no formal theory for the force straining against those pipe walls. And the water inside isn't resting. It just plunged more than 600 feet straight down into a valley. And it is about to climb the far slope and come out hundreds of feet up the other side, with nothing pushing it but its own weight. Everyone hands the credit for this to Rome. The pipe near Pergamon predates many of the grand Roman aqueducts people picture, and it wasn't Roman at all, it was Greek. Hellenistic engineers ran that pressurized line off a ceramic pipeline more than 25 miles long, carrying spring water down out of the highlands to the very edge of the valley. At the valley, they made a decision that should have been impossible for the time. Instead of building a bridge across the gap, they sealed the water into pipe and let it fall. Water that falls 600 feet arrives at the bottom with violence. The pressure at the low point is the kind of load that bursts fittings in a modern house. They knew it would try to tear the pipe apart, and they built for it anyway because a sealed pipe diving through a valley was cheaper than a stone bridge tall enough to keep the water level. The ancients only understood gravity idea dies on that mountainside. They understood pressure. They wrestled with it, lost pipes to it, and won often enough to run a city's water through a pressurized line 1,000 years before anyone drew a proper diagram of how it worked. Which raises the real question. The one this entire story turns on. Every system you're about to see solved the same brutal problem, and it wasn't stone or distance or mountains. It was energy. These people had none. No electricity, no engines, not one unit of power to spend on moving water. Every drop climbed, dropped, turned, and held pressure, using nothing but the shape someone carved into the ground. They got so good at it that one of these channels quietly recorded something for 8 centuries. A record nobody could read until a few years ago, sitting in plain sight inside the very thing everyone assumed was just a failure. Keep that channel in mind. It pays off at the end. Start with the slope, because the slope is where the myth is thickest. In southern France, the aqueduct that fed the Roman city of Nimes runs about 31 miles and drops a total of 56 feet. That's the whole descent. 56 feet spread across a marathon's worth of stone channel. On average, the water falls around 21 inches for every mile it travels. A grade so shallow that if you stood in the channel, you would swear it was dead level, and the water was simply choosing to move. The part that gets flattened into a fun fact is the part that actually matters. That gentle slope isn't even. The engineers didn't lay one clean grade from the spring to the city. They ran the water steeper up top near the source, and then, on the approach to the famous bridge, they nearly flattened it out, down to a fall of about 1/4 of an inch across the length of a football field. Water crawling through a channel so close to level that a strong breeze could have pushed it backward. That wasn't sloppiness. It was a trade. The bridge, the Pont du Gard, the 3-tiered giant everyone photographs, had to hold the water at a precise height to clear the river gorge. If the slope had stayed constant the whole way, the water would have arrived at the crossing too high, and the bridge would have needed to be about 20 feet taller. 20 extra feet of hand-cut stone stacked across a river valley is enormous cost and enormous risk. So they spent their precious few feet of drop early, banked the height, and coasted the water in almost flat. They were trading gradient for stone, doing the math on a spreadsheet made of rock. The mountain, it turns out, was rarely the worst enemy. On that same route into Nîmes, the surveyors ran their line and hit something a mountain at least sits still for, a lake. Not below the channel, above it. The water surface sat about 10 feet higher than the level the aqueduct needed to hold. Going around it meant adding roughly 12 miles of channel through difficult ground, which was out of the question. So they didn't go around the lake. They drained it, they removed an entire body of standing water from the landscape because it was 3 feet too tall, and then they laid their channel through where it had been. And once the water was finally running, the fight didn't end. It changed shape. Spring water in that region is loaded with dissolved lime, and the channels needed constant cleaning by crews called circuitores, men who crawled the length of the conduit on their hands and knees, scrubbing the walls by hand. Roots found their way through the stone lids. Where roots came in, so did bacteria. And the bacteria did something that sounds invented. They grew rock. A living process the sources call biolithogenesis, organisms depositing hard mineral crust inside a working water channel, slowly choking it, closed from the inside while men crawled through the dark, trying to scrape it back open. Hold the crust in your mind, too. It comes back. Back at the pressurized pipe, there was a second enemy nobody talks about, and it isn't pressure, it's air. A single trapped air pocket inside a full pipe can stop the entire flow. The water hits the bubble compresses and shoves back, and a line that should run silent starts to buck. Roman engineers knew this. The architect Vitruvius describes vents built into the pipes. He calls them colliviaria, most likely there to bleed off trapped air before it could seize the line. On the biggest pressure crossings, like the siphon at Aspendos in Turkey, they went further and built tall intermediate towers into the run, structures that split one long, crushing pressure line into shorter stages, easing the pressure and surge instead of letting it hammer a single low point until it failed. That surge has a modern name: water hammer. The bang in your walls when a valve shuts fast and a column of moving water slams to a stop. It cracks municipal pipes today with steel and sensors and pressure relief valves standing guard. Engineers 2,000 years ago felt the same shock coming through cast lead, understood roughly what it was, and designed structures specifically to absorb it. That's not luck. That's fluid dynamics, learned the hard way by people burying their mistakes underground where the next crew would inherit them. Everything so far bent water across a landscape. The Greeks on the island of Samos did something colder. They went straight through the mountain. In the 6th century BC on Samos, an engineer named Eupalinos was told to bring water from a spring on the far side of a ridge into the city. Going around wasn't good enough, so he drove a tunnel, about 3,400 feet of it, clean through the heart of Mount Castro. And to save years, he started digging from both ends at once, two crews boring toward each other through solid rock, blind, with a mountain between them. Think about what that requires: two teams, each in total darkness, each having to hold a line and a level precisely enough to meet a crew they cannot see, hear, or signal, somewhere deep inside a mountain. Miss by a few feet in any direction, and the two tunnels slide past each other in the dark and never connect. Eupalinos knew he couldn't guarantee a perfect head-on meeting. No one could. So he engineered around the failure. Near the center, he deliberately bent both tunnels, a planned kink in the line, so that instead of risking two shafts running parallel and missing forever, the paths would angle toward each other and cross. If you can't promise you'll hit, you promise you'll intersect. The two crews met inside the mountain. The tunnel carried water for centuries, for scale on what that meeting actually meant. In 1994, British and French crews dug the channel tunnel toward each other under the sea, with lasers, satellite positioning, and computers checking every foot. When they broke through, their two bores were off by only about a foot, and that was celebrated as a triumph of modern surveying. Eupalinos closed the same kind of blind gap with sightlines and geometry by the light of oil lamps. None of this was a Mediterranean monopoly. The assumption that mountain waterworks are a European story falls apart high in the Andes. Near Cajamarca, in Peru, a channel called Cumbamayo runs across the mountains, and it was carved as far back as 1500 BC. That's more than 1,000 years before Rome laid its first aqueduct. There was no contact, no shared blueprint, no borrowed engineer. A completely separate civilization, working an ocean away, arrived at the same fight with water and mountains. And they didn't build their channel on top of the ground. They cut it directly into solid volcanic bedrock, chiseling a waterway into the mountain itself. Cumbamayo crosses a pass at the Continental Divide, the spine of the land where water on one side drains toward one ocean and water on the other side drains toward the other. They tapped that line and moved water deliberately across it. And they carved the channel in sharp, deliberate zigzags, angular turns, back and forth. Those aren't decoration. Water picks up speed and energy as it runs, and fast water tears a channel apart. Each sharp turn breaks the water's momentum, bleeding off that energy through turbulence and sparing the stone. They engineered erosion control into the shape of the path. Then there's the part that keeps archaeologists arguing. Cumbamayo is longer than it needs to be. It winds and detours and folds back far more than moving water from point to point would ever require. The leading suspicion is that the channel wasn't only practical, that carrying water across the divide was sacred, and the route itself was part of a ritual, a shape meant to be walked and witnessed as much as used. The most radical idea in ancient water engineering wasn't a bridge or a tunnel at all. It was refusing to let the water see daylight in the first place. In Persia, engineers built qanats, and a qanat is almost the opposite of an aqueduct. Instead of carrying water across the surface on stone, they went underneath and tapped it at the source. A qanat is a gently sloped tunnel, dug by hand, that reaches back into the base of the highlands until it hits groundwater, then guides that water downhill through the earth for tens of miles to fields and towns far out on the dry plain. Above it, a line of vertical shafts drops down to the tunnel, and the deepest one, the mother well at the source, can reach hundreds of feet straight down. Keeping the water underground does two things a surface channel can't. In brutal heat, an open channel loses a punishing share of its water to evaporation before it ever arrives. A buried one loses almost nothing, and a buried line can't be seen. Which mattered more than comfort, as you're about to find out. The men who dug them, the Mekhanis, worked one of the deadliest trades in the ancient world. Down in the dark, in a hand-cut shaft, where a collapse or a sudden inrush of water meant you did not come back up. The knowledge passed from father to son, and it worked so well it refused to die. Qanats spread out of Iran across half the planet, into Oman, across North Africa, into southern Spain, all the way to the Kharez of western China. Some are still delivering water today. One is thought to have been running for some 2,700 years, which is the quiet indictment underneath this entire story. These systems moved water across mountains and deserts for millennia on zero energy. No fuel, no power, no pump. Then modern people arrived with diesel and electricity, drilled straight down, and started pulling groundwater up with motors, faster, easier, and completely dependent on a running engine and a fuel bill. Across the Qanat's whole range, the ancient lines were abandoned for pumps. We didn't lose to the old engineering. We walked away from it because a machine felt more modern than a tunnel that asks nothing and runs forever. There's one more reason those Persian lines went underground, and it turns water from infrastructure into a weapon. Go back to the tunnel on Samos. Driving water through the heart of a mountain was staggeringly hard, but it also meant the city's water supply ran hidden inside solid rock. An enemy laying siege couldn't find it, couldn't foul it, couldn't cut it. A surface aqueduct is a throat any army can reach for. A buried line is a secret, one worth years of extra labor, boring through solid rock rather than raising an open channel in plain view. In a world where you could lose a city by losing its water, hiding the water was as strategic as moving it. The Qanat, invisible under the sand, was doing the same job. A supply line an army could march over and never know was there. So the shape in the ground was the pressure system, the erosion control, the survey instrument, and the fortress wall all at once. Which brings it back to the crust, the mineral scale everyone would call the failure of these systems. That hard lime coating the cercitores crawled in to scrape, the stuff slowly strangling the channels, turns out to be the most valuable thing the Romans left in those pipes, and they never knew it. It didn't build up as a single dumb layer. It went down in bands, season after season, a new skin of mineral each year, thicker in wet years and thinner in dry. Annual rings, exactly like the rings inside a tree. In a Roman channel that fed Cologne, that crust grew about 8 inches thick. Those 8 inches hold 180 years of continuous record, laid down between roughly 80 and 260 AD. Read the bands, and you can pull out the ancient weather, almost season by season. The wet years, the droughts, temperature swings, even the shudder of earthquakes frozen into the rock. A water bill from the Roman Empire, written by the water itself, sitting untouched for 18 centuries until scientists in this era learned to slice it thin and read it. The people who came after Rome didn't read it. They saw something else entirely. When the empire fell and the channels went dry, medieval builders looked at that thick banded crust and saw not a diary, but a material. Cut across the bands, it came up brown and veined and took a polish like stone. So they quarried it out of the dead aqueducts, sawed it into slabs, and sold it as a decorative marble. Aachen marble, worked into altars and columns and set into the walls of medieval churches. Water scale scraped from a Roman pipe, hardened by the same choking process that once ruined the flow, cut and buffed and mounted in a cathedral as sacred stone. While the record of 1,000 ancient summers sat locked inside the Polish, waiting for someone to finally look close enough to read the rings.